Good day, everyone. I'm Mable from the University of Georgia, and today I'm going to introduce you some photonics approaches for high-speed and broadband spectral scanning. So shown here is the overview of the talk. First, I will show you what's the motivation for fast and broadband spectral scanning, and then we'll talk a little bit about what electronics approaches, like what kind of limitations the electronics approaches are facing right now. Then I'll go through a couple of our photonics approaches which can overcome all those limitations. So I'll introduce mainly three approaches to you. The first one is the instantaneous fluency measurement using photonics. The second one is the fluency to time mapping. And the last one is spectral scanning. So after reviewing the existing approach, I will introduce a more innovative approach, which is even better, which is our approach on the modified spectral scanning based on filtering, wavelength conversion, and filtering using all-optical approach. And then I'll end this presentation with a conclusion and summary. So first, why do we want broadband and high-speed spectral scanning? So the first reason is because real-time awareness of spectrum usage is very important. Many events of interest can be quite transient, and hence we cannot wait long to process or recognize those information. And secondly, we want the knowledge of available spectrum. So on the right is the spectral allocation, right upper corner is the spectral allocation plot. So it looks very crowded and it's packed very closely. However, if you look into the spectral utilization underneath it, actually you can locate quite a number of spectral holes there. That means if we can make good use of those spectral holes, we can have a more effective spectrum allocation, as well as we can prevent traffic congestion. And thirdly, we want to have the knowledge of the presence of non-legitimate users, so that we will have some countermeasure and make our, for example, encryption or singularity approach much stronger to prevent those non-legitimate user attack our system. And also, in this way, we can protect the spectrum usage of legitimate users. So all these things, we want it to be over a really wide swath of bandwidth. We are talking about like tens of gigahertz bandwidth. So because we are doing such a high bandwidth and the demand of high-speed scanning, so the electronics approach actually reaching their limitation. So there are many three approaches in electronics that people have been using to gain the spectrum usage. First is the digital signal processing, DSP, via frequency transformation. So in this way, because of the bandwidth and the speed required in our application, so there's a huge amount of data being generated, and it requires extremely large computational power to process the information. So on the right is a very high-end state-of-the-art real-time spectrum analyzer from Photonics. It's very decent, except that it's relatively slow. So the refreshing rate of the screen is only 292 kilohertz over just 110 megahertz range. So it's relatively slow. And the second approach is the spectrum scanning by countertive radios. So countertive radios will require synchronization between each of those countertive radio, and each of them is scanning a specific frequency range. And because of all the synchronization and signal transmission need throughout those bandwidth, a huge amount of data has to be sampled prior to processing. So that also takes up a lot of computational resources and will be limited by how powerful your computer will be, or a server will be. And the last approach is pretty classic, which is a sweep analysis based on spectral scanning. So that's what we have been using in our spectrum analyzer. So it requires high-speed tuning of the local oscillator or spectral filter, which will govern how fast it is scanned over the bandwidth. The fastest that people has been obtained right now is 1 gigahertz sweep in 1 second. So 1 gigahertz bandwidth, you need 1 second to sweep it. So it's still relatively slow. So it will just sweep in this way slowly, and you obtain your signal after 1 second. So with photonics, we found that it should give you some unique advantages over electronics approach based on two facts. So the photonics can process large amount of data in real time without sampling it, because first, fiber optics or the photonics has a really large capacity. So we are talking about 3 terahertz bandwidth, really flat frequency response. So we can squeeze lots of information there and process it simultaneously. And secondly, photonic devices and their phenomena respond instantaneously. Even they are not instantaneously, they're really fast in tens or hundreds of gigahertz speed. So after talking about the advantages, maybe I can show you the high-level architecture of our photonic system. So first, we have a laser diode shown on the left, an optical modulator, a photonic processor, and a photodetector. So what does the laser diode do? Basically, act as an optical carrier at 192 terahertz frequency. So at the optical modulator, we do an electrical to optical conversion by using the received signal and intensely moderate the amplitude of the optical carrier, so that the copy of the electrical signal will become an optical signal. So we can process it all optically in this optical processor. So what does a photonic processor do? It can do a wide range of things. For example, as simple as a true time delay, or just a phase shifter, or an interference cancellation module, or here I would like to talk about the spectral scanning module, which is all optical. And after we process it using photonics, then we'll convert it back to the electrical signal using the photodetector, so that we can do some post-processing of the signal. For example, if you want to analyze it or you want to transmit it in the electrical domain. So there are 3 major molecular photonics approach for spectrum scanning. First is the instantaneous frequency measurement. So this sounds pretty familiar because electronics approach do have this similar architecture, and it's actually borrowed from electronics. And the advantage of using photonics is that it's very broadband. The bandwidth we can deal with is tens or 20 gigahertz. And the component loss relatively is very small compared with electronics. However, it's not very scalable because each of those branches will only able to recognize a specific frequency. So if you really want to scan through a wide range of frequency, you need a lot of them, and then use an optical switch to switch between each of those branches. So it's relatively complicated and not scalable. So the second approach will be the frequency to time mapping. So basically, we use the dispersion in fiber to convert different frequency into time sample. So what is dispersion? So basically, if you know the prism, if you launch a white light to it, it is split into different spatial position. But in dispersion, instead of splitting it into spatial position, it's actually split into time. So different color come out at a different time. So if you see the illustration on the right, if you have a square wave consists of from red to blue, and after dispersion medium, you'll see in time domain is actually the red will be come out faster, and then the blue will come out slower. So it's just spread over time. So this approach is good, despite the fact that it's actually discrete time sampling, and also the resolution is limited how fast you can gate the signal, which I will describe more in the coming slides. So the third approach will be the spectrum scanning, just like the electronics approach, but in this case, we can scan the whole spectrum, and the latency depending on how fast we tune the local oscillator or spectrum filter, just like the electronics approach. And let's look into more details for each of these approaches. First is the photonics instantaneous frequency measurement. So it is borrowed from electronics, which basically is a two-tap filter. And this is the architecture of the electronics approach. And then it's pretty much we split the signal, delay one of the branch, and then combine it together. And we have an optical version of it, which basically looks like this. So the first part is just like what I described to you earlier about the high-level architecture, which is the electrical to optical conversion. So which consists of a laser and modulator, which takes the wireless signal or RF signal. And then we will use an optical splitter to split into two branches, and then one of the branch will use a fiber or some kind of delay line to delay it, and then we combine it together and detect it using a photodetector. So the problem of this approach is that from the equation on the right, you can see that it's still depending on the frequency of the input signal. That means you need to use a high frequency RF power meter to measure it, which is very costly and also limiting your bandwidth. So there's a slight modification of this approach, which instead of adding the two signals together, they're mixing it, they're multiplying the two signals, so that the output, it will cancel out if you use a low-pass filter, you can just look at the DC component, and then you can tell from what is the power you received at the very end, and you can tell what is the frequency you are getting. So we did some experiment on this and used optical approach to optical implementation of this architecture. So we have two laser diodes combined and launched into the RF the modulator, which essentially converts the RF signal into two different optical carriers. And then we launch it into a device called fiber black grating, which basically is a short piece of fiber like that. It's just 1 to 2 centimeters. So these fiber black gratings, I can make it such that each of the wavelength will be reflected back at different timing, so that it provides the timing delay that I need. And after that, I launch it into a special piece of fiber, only like 38 centimeters long, so that I can multiply the signal through a nonlinear phenomenon called four-wave mixing. So it's just exactly the same as the mixer that we have in the electronics. And then we filter it and convert it back to an electrical signal and use a voltmeter to detect the output. And we were able to obtain a curve like this, which means that the vertical scale is the voltage we received, and the horizontal scale is the corresponding frequency. So by looking at the voltmeter of what voltage we are receiving, we can tell what is the frequency of the incoming signal. So this is the first approach, and the second approach is the frequency to time mapping. So what is frequency to time mapping? Basically is if you have an input signal consists of all the colors, and then there's a step recovery, which essentially gate the signal into a tiny piece. And then you launch it in the dispersive medium, which will make different colors to propagate at different speed. So it will become the right-hand side. It becomes like this. So the red will be here, blue will be here, which resulted from the first gating, and the second gating signal will result here. So red is here, blue is here. So if you look at the upper illustration, this is your center wavelength of the laser. And if you have two frequencies going into the modulator, for example, F2 and F1, it will create two sidebands. One is the upper one for F1, lower one for F1, and the other sideband set is F2 and F2. So with the time gating, you're able to chop out each of the color for a tiny period of time, and then you disperse it. So after dispersion, all these boxes will be offset because of the different colors. So that by determining the time separation of the rising edge of each of the color, you'll be able to tell what is the frequency of the incoming signal. So because of the limitation in the time gating here, so the target frequency is only for 15 to 40 gigahertz. It's not very good for low frequency bandwidth. And the rising edge they has been using is 100. The rising edge of the gating signal is 100 picosecond. And the pulse width is 6 nanoseconds with a representation rate of 12 megahertz. So from this number, you can tell that the information you get is just 6 nanoseconds, but there's a very long dead time, which you cannot tell what's in the spectrum. So that's not a very good way to do this. And showing here is the corresponding result. So from the separation of the falling edge here, you're able to have this lookup table and tell what's the frequency, just like what we did before. And the third approach is a spectrum scanning approach. So basically, you have your signal being swept over time, a couple of times, and in the filter, what you are seeing is a change of color from purple to red, like this. And then if you look at the time domain, it's essentially converting this signal from frequency domain to time domain. So you just need an oscilloscope to look at what's going on, and you're able to tell what's the frequency content. So there are three existing approaches for spectrum scanning using photonics. First is to scan the laser frequency, the optical carrier, such that the whole thing will be moving left and right to different frequency, and you just need a fixed filter to filter out the frequency you want to look at. And the second approach is to using a fiber product filter, which essentially is like two mirrors, and the light will go inside, bounce back and forth, and come out. Depending on the separation of the two mirrors, you're able to filter out different frequency or different wavelengths. However, because it requires mechanical tuning of the separation of the two filters, so it's relatively slow. It's in millisecond range, the tuning speed. And for the third approach is the special filter based on fiber black grating. So as I mentioned before, the grating is just a very tiny piece of fiber, and you can tune the reflection bandwidth, reflection frequency firmly. So if you change it into a hotter, like if you warm it up, then you can shift it to a lower frequency range. If you cool it, then you will be able to shift it in a high frequency range. But because it's firmly tuned, so it's still very slow. So it seems that we are not able to find a narrow bandwidth filter which will provide us with spectral resolution, and simultaneously finding the same filter with high-speed spectral tuning, which provide us with the good scaling speed. So both of these requirements cannot be satisfied in a single filter. So by looking back into all the three optical approaches that we talk about, it seems that none of them can really provide the high-speed tuning and scalability that we need in our applications. So we do need a better approach for our for spectral scanning, a broadband spectral scanning. So why? Back to our motivation is the real-time awareness of spectrum usage that we need, and the knowledge of available spectrum and presence of non-legitimate users. So here I would like to show you my approach, which is a modified spectrum scanning approach, which utilizes filtering, wavelength conversion, and filtering techniques, and tens of gigahertz sweeping speed over tens of gigahertz bandwidth will be obtained. So it's not really real time, but it's really close to real time. And this is the architecture of the approach. So we have the RF signal here. We do an electrical to optical conversion, just like what we did before. And then we use a relatively broadband filter, but can be tuned at very high speed because it's all optical tuning. So it can tune at tens of gigahertz speed to chop out each of the component. And then we do a wavelength independent wavelength conversion here. So all these different colors will eventually convert to the same color here. And because they has been converted to the same color, so what we need here is not a tunable filter, but a fixed wavelength narrowband filter. So fixed wavelength narrowband filter is out there already. It's just they're not tunable. They're not fastly tunable. So by combining all the information you've got here and launch it into an oscilloscope, you're able to reconstruct the spectrum like this. Okay? But right now they're of the same color, but you're able to tell which frequency is which by looking at the timing. So we already developed the filter, the fast tunable filter in the lab, which can sweep at gigahertz speed. So I launch a laser to the notch of the filter and try to tune it, and you can see it tuned really fast. This one is 5 gigahertz, and I can easily tune it at 20 gigahertz. This shows that when there is no voltage applied, then it will be the blue curve, and the red one corresponds to when I apply to a voltage to it to show the spectrum tuning. And as you know, we do need a higher order filter to provide a better resolution. So here I try to simulate from a first order filter all the way to a fourth order filter, and we plan to build it in the lab experimentally. So as you know, I'm a junior faculty here, so shown here is the agenda of the work that I'm going to work on. First, I will identify and quantify the photonic subsystem, which include constructing a fast sweeping high order optical spectrum filter that I described to you earlier. And then this filter will be tunable optically or electro-optically, so it will be at gigahertz speed. And then we'll build a wavelength independent wavelength conversion approach, which will study the linearity, signal quality, and spectrum uniformity. And then we'll develop and optimize the spectral scanning system by prototyping it using the subsystem that we built. And then we'll study different system performance and the different modulation approach that we can have. And finally, I will improve the signal to background ratio by removing the cosine interference at the antenna through an optical cancellation system that we have in the lab. And we'll incorporate it and measure the system performance and study the multipath interference. So this is a summary I have. So we want to have the real-time spectral usage wellness that can be achieved. I also found that the photonics is a promising approach because of the broadband, high switching speed, low loss, and low lightweight characteristics. And we are developing this spectral scanning filter, a spectral scanning system, which has tens of gigahertz switching speed and tens of gigahertz sweeping bandwidth based on the filtering, wavelength conversion filtering approach. So this is all I have for today. Thanks for your attention.